Welcome to Inorganic Chemistry. Today, we are diving into one of the most fascinating and foundational topics in quantum mechanics, the significance of wave functions. If you have ever wondered how we can possibly understand the behavior of an electron when we cannot even see it, you are in the right place. We will build this concept from the ground up, so do not worry if it sounds intimidating right now. By the end of this session, you will see exactly how this mathematical tool unlocks the secrets of atomic structure. Let us start with a simple analogy. Imagine you are trying to catch a firefly in a dark jar. You cannot see exactly where it is at any given millisecond, but you know it spends most of its time near the bottom, where you placed some sugar. If you were to write a mathematical equation to describe the firefly's movement, that equation would be like a wave function. In quantum mechanics, a wave function, represented by the Greek letter psi, is simply a mathematical expression that contains all the information about an electron's behavior in an atom. It is the solution to the famous Schrödinger wave equation, which describes how the quantum state of a physical system changes over time. Now that we know what a wave function is mathematically, we must address a crucial point. By itself, the wave function has no direct physical meaning or physical reality. Just like a weather map is not actual rain, but tells you where rain is likely to fall, the wave function is not a physical object you can touch. It is merely a mathematical amplitude, much like the height of a water wave. Its value can be positive, negative, or even a complex number involving imaginary parts. Because we cannot measure a negative or imaginary probability in the real world, the wave function alone cannot tell us the exact location of an electron. This brings us to a brilliant breakthrough by the famous physicist Max Born. He solved the problem of the wave function having no physical meaning by simply squaring it. He proposed that the square of the absolute value of the wave function represents the probability density of the electron. Probability density simply means the chance of finding the electron in a very tiny specific volume of space around the nucleus. In other words, it tells us how tightly packed the chances of finding the electron are in one specific spot. The wave function acts as an information vault, and squaring it is the key to extracting observable properties. Let us look at the mathematical form of this concept. The formula is P equals the absolute square of psi times dV. Where does this come from? Since the squared wave function gives us the probability density, which is probability per unit volume, we must multiply it by a specific volume to get a tangible probability. In this equation, P is the actual probability of finding the electron. The symbol absolute psi squared represents the probability density. Finally, dV stands for the tiny volume element we are investigating. If the probability density increases, the chance of finding the electron in that spot goes up. If we look at a larger volume dV, the total probability P also increases. Before we move on, let us see this with a concrete example. Suppose the probability density of an electron at a specific point A is 0.05. What is the probability of finding the electron in a tiny volume of 2 cubic units located exactly at point A? We are given the probability density and the volume, and we need to find the total probability. We know that probability density is the probability per unit volume. To find the total probability in a specific tiny volume, we simply multiply the probability density by that volume, using the Born interpretation formula we just learned. Continuing with our calculation, we substitute the given numerical values into our equation. The probability density is given as 0.05. The volume is given as 2 cubic units. We place these numbers exactly where their corresponding symbols are in the formula. Multiplying 0.05 by 2 gives us 0.10. This decimal value is equivalent to a 10% chance. Physically, this means that if we look inside that specific 2 cubic unit box at point A, there is a 10% chance we will find the electron there, and a 90% chance it is somewhere else. Let us apply this to another scenario involving a node. An electron in a 2p orbital has a wave function value of exactly 0 at the nucleus, where the distance r is 0. What is the probability of finding the electron exactly at the nucleus? First, we need to determine the probability density at the nucleus. According to quantum mechanics, the probability density is always the square of the wave function. A point where the wave function is exactly 0 is called a node, which is a region of empty space. We take the given value of 0 and square it to convert the raw wave function into a meaningful physical probability density. Now we finish the calculation for the node. The mathematical square of 0 is simply 0. This result tells us that the probability density at the nucleus for this specific orbital is exactly 0. There is no density of the electron cloud at this exact point. Next, we multiply our probability density of 0 by any tiny volume dV. The resulting probability is mathematically forced to be 0. Physically, this means it is completely impossible to find the 2p electron exactly at the nucleus. The electron simply does not exist there. It must exist somewhere else in the surrounding electron cloud. So we have seen how to calculate probability in a tiny volume. This brings us to an important logical rule called normalization. Normalization is a formal way of saying that the electron must exist somewhere in the universe. If we calculate the probability of finding the electron in every single tiny volume across the entire universe and add all those chances together, the total probability must equal exactly 1 or 100%. If the total probability is 1, it means we are absolutely certain the electron exists somewhere around the atom, proving that our mathematical model is physically valid. Now that we understand the concept of normalization, let us look at its mathematical formula. The formula is the integral of the absolute square of psi with respect to volume equals 1. Conceptually, this is just the mathematical translation of adding up all probabilities to get 100%. The integral sign, which looks like an elongated S, means we are adding up the probabilities over all possible space. We integrate from negative infinity to positive infinity to cover the entire universe. The absolute square of psi times dV is the probability in each tiny volume. Setting this entire sum equal to 1 ensures the electron definitely exists. To make these mathematical ideas concrete, let us look at a visual representation. On the screen, you see two side-by-side graphs comparing the wave function and the probability density for a 1s orbital. The horizontal axis represents the distance from the nucleus, labeled r. The vertical axis on the left graph is the wave function psi, while on the right it is the squared probability density. Notice how the wave function curve on the left spreads out further and decays exponentially. However, the squared probability density curve on the right drops off much more sharply. This sharp drop-off visually demonstrates that the electron is overwhelmingly most likely to be found very close to the nucleus. You might be wondering, why does all this complex math matter? The significance of the wave function and probability density is the entire foundation of modern chemistry and electronics. Without understanding probability density, we could not understand how atoms bond together to form molecules like water or DNA. When two atoms come close, their wave functions overlap, and the probability densities dictate whether a strong chemical bond will form or if the atoms will repel each other. Furthermore, this probabilistic nature of electrons is exactly how semiconductors and computer chips work. Engineers use these wave functions to design the microscopic transistors in your smartphone, controlling exactly where electrons are likely to flow. We have covered a lot of ground today, so let us reinforce the three most important ideas. First, the wave function is a mathematical tool that describes an electron's quantum state, but it has no physical meaning on its own. Second, its true significance is unlocked when we square it to get the probability density, which tells us exactly where an electron is most likely to be found. Finally, this probabilistic model completely replaces the old idea of fixed planetary orbits with modern, realistic electron clouds. You have now mastered the fundamental significance of wave functions, a crucial step in understanding the quantum world.